Good morning, everyone. I am Vinita, working as an associate professor in the Department of Electrical and Electronics Engineering, RMD Engineering College. Today in PSA 4th unit, let us see the problem in sequence networks. A 50 MVA 11 kV synchronous generator has a subtraction reactance of 20%. The generator supplies two motors over a transmission line. The transmission line with transformers at both ends as shown in figure. The motors have rated inputs of 30 and 15 MVA, both 10 kV with 25% subtraction reactance. The three-phase transformers are both rated 60 MVA, 10.8 or 121 kV with leakage reactance of 10% each. Current limiting reactors of 2.5 ohms each are connected in the neutral of the generator and motor 2. The zero sequence reactance of line is 100 ohms. Draw the positive, negative and zero sequence network. So in this network actually, there is one generator and two motors are connected through a transmission line and two transformers T1 and T2. And here the ratings for every component is specified in the problem. And we need to draw the sequence network for positive, negative and zero sequence components. So first, we need to calculate the per unit reactance of each and every component in this single line diagram. So for that, first we have to assume the MVA value as well as KVB value. In the problem, it is not specified anything regarding new MVA and KV, so that so let us assume the generator values are taken as the base values. So here the generator values given as 50 MVA, 11 kV and its reactance is 20%. So MVAB new is equal to 50 and KVB is equal to 11 kV. So here first we can draw the single line diagram with the ratings of all the components, and let us assume MVAB new is equal to 50 MVA, and for the same generator the KVB that is equal to 11 kV. So this MVAB that will remain same throughout the problem. So that is from the generator towards till end of this motor calculation, MVAB new remains same. So now the next step is nothing but for each and every component we have to we have to divide the single line diagram into various sections, and for each and every section we have to calculate the new KVB. So like first unit problem, here also we have to divide the problem into various sections. So wherever we have the transformers, we have to divide that into sections. So this is section 1, from generator till transformer primary, it is section 1, and from transformer secondary till second transformer primary, section 2, and then transformer secondary, and then the entire motor sections. So that will be section 3. Now for each and every section, we have to calculate new KVB. So for the first section, since the generator values are chosen as base values, the KVB new that remains same, that is equal to 11 kV. So coming to section 2, here this transmission line that will be connected to high voltage side of the transformer T1. So what is the formula we can apply here to calculate new KVB? KVB on HT side of transformer T1. So what is the formula to calculate this KVB? KVB on LT side of transformer T1 into HT voltage rating divided by LT voltage rating. So if you see here, so what is KVB of LT side of transformer? So it is nothing but 11 kV. You should not consider this 10.8 kV. So this is this 10.8 kV is the old value. But for this section, we have calculated new KVB. It is nothing but 11 kV. So this 11 kV has to be taken for this KVB on LT side of transformer into, for this HT and voltage rating, we have to take this 10.8 divided by 121. So the formula, the equation becomes 11 into HT side is 121 and LT side is 10.8. So if you substitute and simplify, the answer will be 123.2 kV. Similarly, we have to calculate the per unit reactance of the third section. So for this for section 2, its kVb mu is equal to 123.2. Next, coming to the third section, we have to take the kVb on LT side. So till this 121, already it is over. Now here the left out portion is nothing but transformer T2 secondary and motors M1 and M2. So these two motors will be connected to transformer T2 secondary, that is low tension side. So we need to apply formula for kVb on LT side of transformer T2. So the formula is kVb on HT side of transformer T2 into LT voltage rating divided by HT voltage rating. So here this LT by HT ratio is nothing but the transformer actual ratio of 10.8 divided by 121. Now, what is this kVb on HT side? So whatever the value we have calculated previously, HT side. Now, what is the voltage value? 123.2. That voltage we have to substitute now in this formula for the calculation. So if you simplify and get the expression, you'll be approximately getting 11 kV. Now for section 3, new kVb, that is equal to 11 kV. Now we have calculated kVb new for every section. So after calculating kVb, what is the next step? We have to calculate the per unit reactance of every component. So first one, generator. So for generator, what's the formula to calculate Z per unit? That is mu is equal to Z per unit old into kVb old by kVb mu the whole square into MVAB new divided by MVAB old. So here for this for each and every component we have to calculate the positive, negative and zero sequence component separately. Normally the positive and zero negative component will remain same and zero sequence component that will differ. So if the value of X per unit old, which is commonly given for positive and negative, we can calculate it by using the same formula. If positive sequence 1 is per unit old and for negative sequence another one is per unit old, means we have to separately calculate the value of positive and negative sequence. So let us refer the problem positive and negative sequence component of generator. See here xg1 xg2. xg1 represents positive sequence component and xg2 represents negative sequence components. So here xg1 xg2 that is equal to 20% and xg0 that is equal to 6%. So that means positive and negative sequence reactance remain same and the zero sequence reactance that is 6%. So we can use the same formula to calculate positive and negative sequence reactance and we need to calculate zero sequence reactance separately. So for generator, for this generator, we can calculate the value of positive and negative sequence reactance, that is Z per unit mu. Z per unit old into kVb old by kVb mu the whole square, MVAB old divided by MVAB new divided by MVAB old. So for this generator, Z per unit is given as 20%. So it's J.2 into kVb old for generator is 11, mu is also 11. So 11 divided by 11 the whole square into MVAB new is 50 and old is also 50 for generator. So its value will not change. It's J.2 per unit. Next, the same formula we can calculate for zero sequence reactance also. So zero sequence reactance is per unit mu that is equal to, we have to substitute its value. So for zero sequence reactance, it is given as 6%. So if it is 6%, it is J.06 into its corresponding kVb old and new as well as MVAB new and old. So these values that remain same, only there is a different reactance given for this zero sequence. So we can take this 6% to calculate zero sequence reactance of the generator. Now we have calculated positive sequence reactance, zero sequence reactance and neutral reactance. So after calculating this, since the generator which is connected through neutral reactants. Here, Xn value is given. Xn is the neutral reactants. So the generated neutral that will be connected to the ground through the reactant. So we have to calculate separately the value of Xn. So Xn formula is 3 into Xn. So 3 times the value. Here we have calculated the value of zero sequence reactants. So 3 into 1.033 becomes 3.099. This is for generator. For generator, we have calculated positive, negative, and zero sequence reactants. Next, we can calculate the value for transformer 1. For transformer, again, the same formula. If the values are given in per unit, we have to use the formula Z per unit mu is equal to Z per unit old into kVb old by kVb new the whole square into MVAB new divided by MVAB old. So for this transformer, in the data actually, if you see for transformer T1, generally it is given X is equal to 10%. So they have not specified about positive, negative, or zero sequence. Generally it is given so that we can calculate reactants for the general formula. That is only one time we can calculate the reactants. So this positive sequence that will be equal to negative sequence that will be equal to zero sequence reactants. So we can substitute the value here. If it per unit old value, it is J.1 into kVb old for transformer 1. What is kVb old? What is kVb new? And then MVAB new is 50 and MVAB old is 60. So if we substitute all the values, we can calculate the value of per unit reactant, that is positive sequence, negative sequence, and zero sequence reactant of transformer. And then for transmission line. So for transmission line, the kVb new we have calculated is 123.2 kV. It is kVb new value. Since the value of the transmission line reactance given in terms of ohms, we have to use this formula to calculate per unit reactance. Is that per unit mu is equal to is actual divided by actual value divided by base value. So what is the formula for base value? kVb mu the whole square divided by MVAB. So if you rewrite the expression, the formula becomes is that actual into MVAB mu divided by kVb mu the whole square. Now we can use this formula to calculate the value of per unit reactance of transmission line. In this transmission line also, for positive and negative sequence component, the reactance value is given as J100 ohms. And for zero sequence reactance, it is given as J300 ohms. So we have to calculate these two reactances separately. Positive and negative sequence reactance that is equal to actual value. So actual value is nothing but the value given in the problem itself. So it is J100 ohms into MVAB mu is equal to 50 divided by kVb mu that is equal to 123.2 the whole square. So if we substitute all the values, we will be getting this value. Similarly, for zero sequence reactance, the value given is J300. So again, we can substitute and get the answer for zero sequence reactance. This is for transmission line. Next one is transformer. So the same formula for transformer is that per unit mu is equal to is that per unit old into kVb old by kVb mu the whole square into MVAB new divided by MVAB old. And here also all the values are given same for positive, negative, and zero sequence. So you can substitute. So for transformer XT1 that is equal to XT2 that is equal to XT0. So all the sequence reactances are same. So that we can use we can calculate the reactance value by using the same formula. So here all the values are same and the answer is J 0.0805 per unit. Next, after calculating transformer T2, we have to calculate for motor 1 and motor 2. So if you go for motor 1, for this section, kVb2 that is equal to 11 kV. And we can use the same Z per unit mu formula. And here also for positive and negative sequence, the reactance value given is 25%. And for zero sequence reactance, its value is given as 6%. So we can substitute the formula. Only difference is nothing but this Z per unit old. So remaining data set is KVB old, new, and MBAB new, old, and all. You have to refer the particular component and then you can substitute here so that you can calculate positive and negative sequence reactance. Similarly, if you substitute Z per unit old for zero sequence, we can calculate the value for zero sequence reactance. And then MOTA 2. MOTA 2, it is like MOTA 1 only, and only same KVAB old and KVAB new remains same because both will be connected in the same section. And MBAB new by old, that is also 50 is new, and for the corresponding MOTA, it is 15. So the formula becomes, so only variable is nothing but is the per unit older. For this positive and negative sequence, it is 0.25, that is 25%, and for zero sequence, it is 6%. Now we have calculated all the reactance value. So after calculating all the reactance value, what is the next step? And before that, for motor also here the neutral reactance value is given, and for reactance value we have to calculate this separately 3 into xn. Like generator, here also we have to calculate the value of 3 into xn, which is 3.099. Now, after calculating all the reactances, we need to draw the reactance diagram. That is positive sequence, negative sequence, and zero sequence. All the three reactance diagram we have to draw. So, while drawing the positive sequence network diagram, the generator and motor that will be represented by its source along with its reactance. Only for motor and generator, it should be represented by the source and its reactance. Remaining all the components like transmission line, transformers, all those things that will be represented only by its reactance alone. And here, this is the reference bus. And from the reference bus, so initially generator will be connected, generator source and its reactance. So whatever the value of sequence reactance value we have calculated, that is xg1, that value we have to substitute here. And similarly, after generator, there will be a transformer T1, then transmission line, then transformer T2, then motors, motor 1, motor 2. So since already all the values are calculated, you have to draw the positive sequence network diagram, and then you have to mark all the reactance values in the reactance diagram. And the values, the reactance values are specified in the problem. It's nothing but in subtransient values. So that here the motor, that is all the values are represented by double dash. So if it is a subtransient reactance, then you have to represent every value by double dash. If it is a transient reactance, then dash. If it is a synchronous reactance, then it will be represented by AGM, like that. So this is positive sequence reactance. Next, coming to negative sequence reactance. Here, we have to short the source for generator and motor. So in the positive sequence reactance only, we have to represent the generator and motor by its source. Remaining negative sequence as well as the zero sequence network diagram, we should not include the source for generator and motor. So here the sources are shorted. That is, the generator source and the motor sources are shorted. Only it will be represented by its reactance value. Same, the positive sequence diagram and negative sequence diagram is similar only, but only thing is in negative sequence there is no source. And coming to the zero sequence network diagram, depends upon your star and delta connection. We have to draw the zero sequence diagram. So first one is generator. So we can refer the diagram, first diagram. So in your problem actually, for generator, it is star connected with neutral grounded. And here the transformer T1 primary is delta connected. So the current will flow through the circuit only when there will be a ground connection. So for generator, it is grounded, and for transmission line T1, it is a delta connection. So delta connection means current will be circulated only within the delta. It will not flow through the transmission line. So here, while drawing the zero sequence reactance diagram, here generator, and its generator reactance, and then transformer primary reactance. Since the transformer primary is delta connected and there is no current flow through the circuit, it is drawn as open circuit in the diagram. Here there is no current in the delta connection. From the delta, only inside the delta there is a circulation of current, and the current will not flow through the transmission line. So it is drawn as or it is mentioned as open circuited. And then secondary of the transformer, if you see the secondary of the transformer is transformer T1 is star with neutral grounded through the star with neutral grounded, and T2 also star with neutral grounded through the transmission line. In between T1 and T2 there is a transmission line. Since the T1 star is grounded and T2 star is grounded, the current will be flowing through the transmission line. So here this is transformer T1 reactance value, then transmission line, and then T2. Since both that is both transmission T2 second, T1 secondary and T2 secondary, both are star with neutral grounded, then the circuit or the circuit will be like a closed circuit and it will be carrying the current. So while drawing the circuit from this reference towards the, since the transformer T2 secondary, it will be like short circuited. So here until this transformer secondary, it is short circuited. Now from transformer T2 secondary, so till this now it's over. Now transformer T2 secondary is delta connected, and here for motor, only for the motor M1 only it is star connected, and motor M2 the star with neutral grounded. So here only for this motor 2 there is a path for the current flow, and for transformer T2 and motor 1 there is no provision for the current flow. So we can see how it will be represented. So for transformer T2 secondary, it is delta connected, so there is no current. So here this point is open circuited, and then motor M1 and motor M1 again it is only star connection, that also will not carry the current. So here that is for the entire connection, it is open circuited. J 3.1, J 1.164. We can 0.164 is nothing but the zero sequence network of the motor 2. And what is the second value? This is motor 1, 3.10. 3.10. So we have three components actually. Here in the secondary side we have three components. So one is transformer 2, and second one is motor M1 and motor 2. So for motor 2, what is the reactance? This for motor 2. Motor 2, the reactance is 3.099. 3.099 is nothing but approximately 3.1. So motor 2 and the reactance motor 1 that is connected, and then it will be connected in parallel with the transformer T2 reactance. So since this is delta connected, it is open circuited. Anyway, for the secondary, for section 3, there is no current, and so the circuit that will be in open circuit condition. There is no current in the circuit. So this is about zero sequence network. So only positive and negative sequence network would positive and negative sequence network is very simple. So only we have to concentrate about this zero sequence network. The current will be flowing through the network only when the neutral of the star, which is grounded. Then only the circuit will be closed and current will be flowing through the circuit. Only that case we have to consider while drawing this zero sequence network.